I am Devasri from Pondicherry University. Today, the topic of my presentation is LP norms on Rn spaces. I think we all are familiar about the norms defined on vector spaces. We define norms on vector spaces to measure the length of the vector. Here, today we see about LP norms on Rn, which is one of the simplest norms in Rn to work with. We define LP norms as the follows. For p greater than or equal to 1 and less than or equal to infinity, we define LP norm as summation modulus of xi power p whole to the power 1 by p for 1 less than or equal to p less than infinity. And for the p infinity case, we define it as maximum of norm of modulus of xi, where I varies from 1 to n. We usually call this as LP norm or sup norm. Okay. Now we defined norm for p greater than or equal to 1 and less than or equal to infinity. So why can't we define for p less than 1? What will happen if we define norm like this for p less than 1? If you are defining a norm on a vector space, it should satisfy 4 properties. But in case of p less than 1, it will violate one of the norm properties called triangular inequality. Let's see with an example. Consider in R2 space, consider these two vectors, x bar equal to 1, 0 and y bar equals to 0, 1. Now, triangular inequality says norm of x bar plus y bar will be less than or equal to norm of x bar plus norm of y bar. If we work at the left hand side, it is coordinate wise addition. So it is 1 power p plus 1 power p whole to the power 1 by p, which is 2 power 1 by p. The right hand side we can illustrate as norm of x power p plus y power norm y bar is equals to 1 power p plus whole to the power 1 by p plus 1 power p whole to the power 1 by p, which is equals to 2. Since we consider it as p less than 1, 1 by p will be greater than 1. So obviously 2 power 1 by p will be greater than 2, which violates the triangular inequality. So we cannot define this LP norm for p less than 1 case. Now, as I already said, if we are defining a norm on a vector space, it should satisfy 4 properties. The following are the 4 properties. Let's verify one by one. First property is the non-negativity property. It is for every vector in the vector space. Here the vector space is Rn. So for every vector x bar in Rn, the norm LP norm of the x bar should be greater than or equals to 0. Now, to prove this, we already know that modulus in R, modulus is always greater than or equals to 0. We know that, right? So for any I, modulus of xi is always greater than or equals to 0. So if we raise p power to that modulus, it still be greater than 0, greater than or equals to 0. And adding those modulus each xi's will not change the non-negativity. So ultimately, we get the modulus of norm of x bar is greater than or equals to 0 for every x bar in Rn. Let's move to the second property. Second property says norm of x bar is equals to 0 if and only if the vector x bar is equals to 0. Now consider the norm of x bar is equals to 0. What it says? Summation modulus of xi power p whole to the power 1 by p is equals to 0, which implies summation modulus of xi power p is equals to 0. As we already know, modulus is non-negative. Modulus of xi is always greater than or equals to 0. It is positive quantity. So adding all the terms is equals to 0 means each of the terms should be equals to 0. So for any I, for I from 1 to n, mod of xi is equals to 0, which means all the coordinates are equals to 0, which implies x bar is equals to 0. If we go from the last, it shows exactly the same. So it is an if and only if condition. So we now proved the second property. Let's move to the next property, which says for any alpha in R and x bar vector in Rn, we have norm of alpha times x bar is equals to modulus of alpha. Here alpha comes from R. So it's a modulus of alpha times norm of x bar. Now we fix the alpha and x bar. Now the norm of alpha times x bar is equals to summation modulus of alpha xi power p whole to the power 1 by p. We know that by the modulus, simple modulus property, we can easily evaluate this. So we are taking out the modulus of alpha power p from each of the, it's a summation, so we can take the term alpha power, modulus of alpha power p, and then taking out, we will get the modulus of alpha times, this is nothing but norm of x bar. These are easy to prove, simple algebra. Then triangular inequality. This triangular inequality is a bit complicated, but it is easy to prove for the case p is equals to 1 and p is equals to infinity case. Triangular inequality says for any two vectors in Rn, norm of x bar plus y bar is less than or equal to norm of x bar plus norm of y bar. Let's see for the case p is equals to 1. For p is equals to 1 case, it is nothing but the sum of modulus of the each coordinate vectors. So if we add these two norms, the coordinates will be x1 plus y1, x2 plus y2, etc. xn plus yn. So we are just adding, and then as we know the property of modulus, by property of modulus, we can just modulus of x1 plus y1 is less than or equal to modulus of x1 plus modulus of y1. We are using those and combining the x terms and y terms separately, and then we will get L1 norm of x bar and L1 norm of y bar. So it is easy to prove. Then for p is equals to infinity case, we know that for the modulus property, for every I, modulus of xi plus yi is less than or equal to modulus of xi plus modulus of yi. This is true for every I. So if we take the maximum of all the among all i's, so this is still be true. This inequality still holds. So then maximum of the all the terms xi plus modulus of xi plus yi is still less than or equal to modulus of xi plus modulus of yi. And this is also true for every I. So we are applying maximum over I for the all the terms modulus of xi. And this inequality will still hold. And again, for yi also, this is true for every I. So we are taking maximum. So in this case, this is the L infinity norm. So now L infinity norm of x bar plus y bar is less than or equal to L infinity norm of x bar plus L sub norm of y bar. So these two cases are easy to prove. Now let's move to the case 1 less than p and less than infinity. This we can't prove directly. We need two inequalities for this. One is Young's inequality and another is Holder's inequality. Young's inequality states that let 1 less than p less than infinity and q is 1 less than q and less than infinity, such that 1 by p plus 1 by q is equals to 1. It is p and q are conjugates. Then for every non-negative vectors x comma y, we have x power p by p plus y power q by q greater than or equal to xy. And then Holder's inequality says if this we have a p and q conjugates, we have if x bar and y bar belongs to Rn, then we have this inequality. Summation modulus of xi yi is less than or equal to this. This is nothing but LP norm and this is nothing but LQ norm. And we are not going to prove this inequality. I'm just giving the hint to prove this inequality. Just consider AJ as modulus of xi by norm LP norm of x bar and BJ as modulus of yi and LQ norm of y bar. Just these we know that these two aj and bj are greater than or equals to 0, and substitute aj and bj in place of x and y in the Young's inequality, and we get this inequality, and adding all the n terms, because this inequality is true for all j from 1 to n. So just add those and you will get the inequality. Now let's prove the triangular inequality for this case. Prove the triangular inequality for the case 1 less than p less than infinity. We call it as Minkowski inequality. To prove this, let's consider the summation of modulus of xi plus yi power p, and just remove, like, just add, like, in the power, write the modulus of xi plus yi power p as modulus of xi plus yi into modulus of xi plus yi power p minus 1. And we know for this modulus of xi plus yi, we can use the modulus property, that it is less than or equal to modulus of xi plus modulus of yi. Now we can separate these terms as summation I from 1 to n modulus of xi times modulus of xi plus yi power p minus 1 plus summation of yi times modulus of xi plus yi whole power p minus 1. Now we know the Holder's inequality, and it is in the form of, these two terms are in the form of summation modulus of xi yi. So we can use the Holder's inequality, and here xi is the same as xi, and yi is xi plus yi power p minus 1. And what Holder's inequality says? Summation modulus of xi yi is less than or equal to summation modulus of xi power p power 1 by p, and summation modulus of yi power q power 1 by p. So just we are applying the same thing here. Remember, p and q are conjugates. This 1 by p plus 1 by q is equals to 1. Now using Holder's inequality, these terms will become summation modulus of xi power p whole to the power 1 by p, and summation modulus of xi plus yi power, that p minus 1 is already in the power, and multiply into q whole to the power 1 by q. Same with the second term. Now this term is common, that summation I from 1 to n modulus of xi plus yi to the power q into p minus 1 whole to the power 1 by q. So just simple rearrangement, we will get 1 by q as p minus 1 by p, and p as q times p minus 1. So instead of q times p minus 1, just substitute p. So we get this inequality. Summation mod of xi plus yi power p is less than or equal to, this is nothing but summation mod xi power p whole to the power 1 by p is nothing but LP no, that by the definition. So just substitute in terms of that mod LP norm of x bar plus LP norm of y bar times summation modulus of xi plus yi power p whole to the power 1 by q. Now we have to eliminate q somehow. So both sides multiply by this term summation I from 1 to n modulus of xi plus yi power p whole to the power 1 by q, because we need to eliminate that 1 by q, that term. So just multiply by this term summation xi plus yi power p to the power minus 1 by q. In this side we already have that term power 1. So if we multiply, it will be 1 minus 1 by q in the power, which is nothing but 1 by p. So summation modulus of xi plus yi power p whole to the power 1 by p is nothing but the LP norm of x bar plus y bar, which is less than or equal to x bar LP norm of x bar plus LP norm of y bar. So we proved the triangular inequality for all the p from 1 to infinity. Now we verified the norm properties for this LP norm. Now we defined LP norms for p from 1 to infinity. So can we compare these norms? Is there any relation between these norms? Let's see. Consider an x bar vector in Rn. Now, we know that each mod xi is less than or equal to maximum of the collection of all xi's, which is nothing but L infinity norm. So if we add all those xi's, modulus of xi's, this is true for every I from 1 to n. So we are just adding all the xi's, which will be less than or equal to summation, if it is from 1 to n, LP norm of x bar. LP norm of x bar is nothing but a constant. It is independent of the n. So we are removing that. It will be n times LP norm of x bar. So this side is nothing but summation modulus of xi is nothing but L1 norm. So we can say L1 norm is less than or equal to n to the n times L infinity norm. This is true for every vector in Rn. So now we estimated L1 norm in terms of L infinity norm. So similarly, if you proceed the same steps, we can able to estimate for L2 norm also. So following the same steps, we will get summation modulus of xi square will be less than or equal to L subnorm, like L infinity norm of x bar to the square, because modulus of xi square will be less than or equal to maximum of modulus of xi square, which is nothing but whole to the square. So it will be L infinity norm of x bar square. So proceeding the same way, it will be summation modulus of xi square is less than or equal to n to the n times L infinity norm of x bar square. Now taking the root so that we can get the L2 norm, we will get L2 norm is less than or equal to n power 1 by 2 times L infinity norm. So now we estimated L2 norm in terms of L infinity norm. We estimated L1 and L2 in terms of L infinity. Let's see for general case. Can we estimate for any P? So we just fix any P from 1 to like 1 from P greater than or equal to 1 and less than infinity. This will be summation modulus of xi power P is less than or equal to summation norm of. This is because maximum. When as we proceed from like this step, the same procedure we are using here. So each xi term is less than or equal to maximum of xi. So it is nothing but L infinity norm. So summation modulus of xi power P is less than or equal to summation L infinity norm of power L infinity norm of x bar power P. So it will be n times L infinity norm of x bar power P. So taking 1 by P, P root, we will get LP norm of x bar is less than or equal to n times 1 n to the power 1 by P times L infinity norm. So now we estimated all the LP norms in terms of L infinity norms. Now let's try to estimate L infinity norm in terms of LP norms. This is easy, right? So maximum of xi, let's say maximum of the collection of xi is some xj for some j in between 1 to n. This xj modulus of xj, we can write it as xj modulus of xj power p whole to the power 1 by p. This single term is less than or equal to summation modulus of xi power p to the whole power 1 by p. Right. So this is nothing but LP norm of x bar. So L infinity norm of x bar is less than or equal to LP norm of x bar. Now we estimated L infinity norm in terms of LP norm. So now we get the inequality like this. L infinity norm L infinity norm of x bar is less than or equal to LP norm of x bar, which is less than or equal to n to the time n power 1 by p times L infinity norm of x bar. So we can conclude that is we can estimate any LP norm in terms of L infinity norm. So we can say any LP norm is equivalent to L infinity norm or sup norm. So we found a way to say two norms are equivalent. Now we define, we say the equivalent of two norms. So two norms, norm 1 and norm 2 are said to be equivalent if there exists a lambda greater than 0 and mu greater than 0 such that lambda times L, one norm of x is less than or equal to 2 norm of x less than or equal to mu times 1 norm of x for every x in x. In this case, lambda is nothing but 1 and mu is n power 1 by p. Now we have shown that any LP norm is equivalent to L infinity norm. But in general, we can also show all norms in Rn are equal. But for that, we need many things to work out. We are not going to prove those things. So in particular, we can say any two LP norms are equivalent. You can refer functional analysis by S. Kumaresan sir and Sukumar sir for the further studies about all the norms of Rn are equal. Now, let's move to the completeness of Rn with L infinity norm. So what is completeness? When we'll say a space is complete, we say a space X is to be complete if every Cauchy sequence in X is convergent in X. That is, if we take any Cauchy sequence in the space, it should converge to a point in that space. To prove the completeness of Rn, let's consider a Cauchy sequence in Rn with respect to L infinity. With respect to L infinity means the convergent and Cauchiness with respect to this L infinity norm. Now, we have to be very careful with the notations because we usually use n for the sequence. Here I am using k for the sequence because we have Rn space. We should not confuse it. So, let's consider a Cauchy sequence in Rn. X k bar, which means x1 bar is equals to x11, x12 up to x1n. We have n coordinates and this sequence is a, for in general, xk term will be xk1, xk2, etc. xkn. So it is a Cauchy sequence in Rn. So saying the sequence xk bar is Cauchy in Rn is equivalent to say each column, that is each coordinate wise Cauchiness in R. If we take each column, for example xk1, if we take, it will be x11, x21, x31, etc. xk1. This is the sequence in R which will be Cauchy. So saying the xk bar is Cauchy in Rn is equivalent to say each column is Cauchy in R. So this is true for every column. So we know that R is complete, right? So if R is complete, then since we said each column is Cauchy, we can find some convergent point for each column. Let's say the convergent point for each column sequence is xj. So we have a vector x1, x2, etc. xn in Rn, which are the limit points of this column sequences. So now, so we have a vector in Rn and we have a sequence xk bar, which is a Cauchy sequence. So let's try whether it works for like this x bar is a convergent point for the Cauchy sequence we took a Cauchy sequence, right? Let's see if it is a convergent point in Rn or not. So saying xk bar converges to x bar with respect to L infinity norm in Rn is same as given any epsilon greater than 0, there exists a natural number such that L infinity norm of xk bar minus x bar is less than infinity for every k greater than or equal to n. With this norm is nothing but maximum of 1 less than or equal to j less than or equal to n. The modulus of xkj minus xj is less than epsilon for every k greater than or equal to n. Okay. Let's start with an epsilon greater than 0. We know that each column is convergent to, each column xkj converges to xj. This is true for every j from 1 to n. So for any j and for the given epsilon, we can find a stage nj such that this modulus of xkj minus xj is less than epsilon after the for every k after that stage nj. This is because we already know that each column sequence converges to xj. Now we have a stage nj for each n. 1, 2, 3. For every j, we have a stage nj. So if we consider the maximum of all these stages, then can we have a stage like capital N? Will this work for our original Cauchy sequence in Rn? Let's consider the capital N as maximum of all these nj stages. Now, maximum of for this n, maximum of x power, because capital N is the maximum of all the nj's, and we know that for each nj, this modulus of xkj minus xj is less than epsilon. If it is true for all nj's, if we take the maximum of all the nj's for this stage capital N, this also true. So for maximum of 1 less than or equal to j less than or equal to n, modulus of xkj minus xj is less than epsilon, which is nothing but L infinity norm of xk bar minus x bar is less than epsilon. Hence we prove that xk bar is the convergent sequence. So x bar is the limit point of xk bar. So now we took a Cauchy sequence. The idea of the proof is we took a Cauchy sequence in Rn and we saw that saying that a sequence is Cauchy in Rn is same as saying that coordinate wise, that column wise Cauchiness in R. So since R is complete, so we can say that column wise sequence is convergent to some point in R. So taking that convergent limit points of all the columns, we found a vector x bar in Rn, and we showed that xk bar is convergent to that x bar. So now we can conclude that Rn with respect to L infinity norm is complete. Now we can have the question. This is we just proved for L infinity norm. So what about remaining LP norms? Is it true? Yes, it is. Because we already proved that LP norm and L infinity norms are equivalent. It is any LP norm is equivalent to L infinity norm. We have proved this for L infinity norm, the completeness of Rn we proved for L infinity norm. So using that equivalence, we can prove the remaining LP norms also. So in general, we can say for any LP norm, Rn is complete. So with this, I'm concluding my presentation. Thank you for all to listen my presentation.